start with an example of my great friends, the company called ONESOIL, with a project of the regional map for the food production. So for many countries, they trained the model and classified the commodity crops production for several years. I guess it's about 3 years for most regions, and that's primarily US and Europe. So really cool thing that it's possible to see how much food was produced, and this includes wheat, soybean, maize, cotton, sugarcane. So what's amazing, I have a very fast GIF in this slide. So they analyze the data on the field level. So one field is like, how many? It's like 12 to 60 to 100 hectares, which is not very large. So they used medium resolution data to see what's happening within the field. So they were talking about the data with a resolution of 10 to 20 to 30 meters, not a 100 meters data, because of the crop rotation. It's really important to see how much surface is covered with this given field to understand what was growing there, was it successful, was it harvested, and did this field bring some input to the food production of the region. So from the field level back to the regional and national level to assess how much, for example, potatoes were produced in US last year, they looked at the very, very deep to the field level. And on the left hand, there is a chart. The chart is called NDVI, and this is basically the way how did they analyze what was growing there. So NDVI is one of the vegetation indexes extracted from the multispectral data. Satellites light the surface of Earth in red, near-infrared, green spectral bands, and by this information, it's possible to extract a metric of NDVI and use this metric to see what was growing there. So it's possible to plot this metric from day to day, from week to week, and see how the crop was developing this year from the comparing to previous year, how this field is performing comparing to the other field, and even do the cool things like crop classification and farming activity detection. So NDVI is just an example of the vegetation indexes. There's like plenty of them, and the reflectance of the green mass in the red and near-infrared bands allow us to see the greenness, the amount of green mass over the field, which finally, at the end of the season, translates into how much sugars or how much starch was produced for this given field. NDVI is just an example of the index. There are really plenty of them, depending on the type of crop, type of temperatures, and most of them use different multispectral or even very narrow hyperspectral bands. And the main input for us from our practice that in order to do a successful machine learning or deploy some neural network with this data, so the best way is to use all these indexes as an input because they're pretty deterministic, and also the values of the raw bands as the features. So this was really the most helpful takeaway from us. So there's not one index better than another. It just use all of them. Some of them would help. And for our company, we realized that a successful project for understanding what is growing. Sorry. Oh my God. Google doesn't like me. To have a successful project to do the crop classification or to do the prediction of how successful field is performing, we identified 3 groups of challenges that the team should address. So one of them is stream of the observation data. So we cannot go to every field and see what's going on there, but we can, to temporal basis, assess the vegetation, assess the temperature, weather, and get some statistical demographical information as frequently as possible. So the second important thing, which is in fact the most important bottleneck which prevents us from having a real very high resolution map of crops, is the ground truth data, which we use for training and validation. Because this data should be relevant, it should represent this given type of crop in this given geography and for this given type of soil. And this data, unfortunately, is pretty rare, and for rural regions, it's a challenge to extract it. And the third part is the challenges associated with the methods of how this type of tasks should be addressed, and they include both the algorithms and the methods. And one of the most challenging for us is the data engineering part, because we are talking about satellite images, which are like a gigabyte per shot, like 100 gigabytes per day. And with this data, there should be certain engineering routines to perform process them successfully. And today I'll focus more on the data part of the problem, and let's start from the observation data. This data should be frequent, and this data should be relevant. So we are talking about weather, optical, radar imagery, and also some of the location-based economical data from demographical, from some statistics we identified it was also useful. So for the multispectral data, the most widely used are the I'll start with the land mapper, which is the data from our own constellation, and also the data from NASA Landsat 8 and ESA Sentinel-2, which allow from 10 to 30 meters resolution, and combined they give up to daily revisit frequency. So the Landsat 8 has the deepest archive, that started with 2013, and for other applications it's possible to look up back to 70s from the Landsat 1. And all this data is like one way or another is also accessible. But this data has a little bit lower resolution. So the ESA Sentinel-2 is really amazing. It has a little bit smaller archive, but it has more spectral bands, higher GSD, and currently it's the really industry standard of the data which should be used.
What is this? What is this river? It's amazing. I need to go there.
It is in Madagascar.
Oh.
I can send you an address because I process it myself. So the radar data, which is also very important, and Sentinel-2 provides it. So radar data basically shows the waters, its main application for agriculture. And it's really possible to identify irrigation from non-irrigation fields, water resources, artificial and natural, and how much data is there available, which also helps to predict how successful is going to be the agricultural activity in this region. This data is available at scale in two ways. So one is obviously going to NASA and ESA native data sources, which has its own challenges because the APIs are not that friendly, there are limits in bandwidth. Or the more cool way is to do the Google or Amazon cloud services, where they have this data available in a pretty nice already processed products. The only challenge is that it covers the full scenes that cover like tens of thousands of kilometers, but overall this data is accessible and it's all open source, ready to use. Obviously there is also a whole bunch of the commercial data, and all these companies, including the company I'm happy to be part of, provide the data with higher frequency, higher resolution, and has more dedicated spectral bands, but in fact this data should be used only when it's really needed. Because for vast majority of applications, Landsat and Sentinel is enough until you really care about some very narrow changes in certain bands. So for example, for cotton, there should be a really very narrow spectrum of red band which shows the phenological phases and how the cotton is performing, though the cotton is a large market itself. Or the data should be done more frequently, because for multispectral data, for the red and near-infrared bands, the main challenge is the clouds, because the agricultural activity active regions, they are often cloudy. And for example, if you have a daily observations for a season, it's a really high chance that half of this imagery will be affected with the clouds, and there is no use in it. So this data is available, and it should be only used when there's a real need in it. Yeah, so our own data. In our company, we build custom satellite missions and put different types of payloads in small sats. And one of this type of the payload is the multispectral camera. We use cameras dedicated to see the vegetation. So these cameras light the Earth in red and near-infrared spectral bands to extract the growing features. And this data is consistent with Landsat and Sentinel, so it's possible to build a continuous time series specifically to do the daily monitoring. Regarding the weather data sources, there are two ways of doing it. One is going to NOAA directly. They have an API, they have a data set, they have historical data for up to 20 years back in history. And the main problem is this data is pretty challenging to extract. Alternatively, there are commercial APIs like these three, like Weather on the Ground, Aerostate, and Weather Decision Technologies. They provide the data in a more agricultural analytics friendly way, but it is pretty pricey, and if it's not like a real regional analysis, probably this data probably then NOAA should be used. And the last type of data we identified really helpful is the demographic statistical data, information of how much food was produced, how much food was sold, consumed in previous years, all these types of indexes. These data sources provide large APIs, pretty nice, and internally we identified that it's faster to deploy them and try to see some correlation between features than thinking that, do we need this or not? So it's really, sometimes it's helpful. And the second part of our equation, of our process, is the ground truth data, is how we put all these observations and what do we use for training the model, or what do we use to identify that these type of features look like corn, or these type of features look like a healthy cotton field. So there are two types of this data. One is we need a lot of almost relevant data for training, and the second part that we need like specific local data for this region, for this type of crop, for this type of seeds, for this soil, to do their validation. So for training, I believe the vast majority of teams who do the crop classification, they use this data set. It is USDA, it is amazing. It has 15 years of history, and it has 6 years of high resolution history with the resolution of 30 meters in 1 pixels. They do the crop classification at pretty high accuracy. So the USDA does this semi-automatic with like 85 to 90% of accuracy, and this data is pretty good training data source. So all the training should be done on this data, and then the tuning should be done on the local data given on the region you're looking at. So yeah, as I said, it's a very high accuracy, 30 meters resolution, and it also has an API. And the last set of challenges is how to use this data and how to do the engineering part of the problem. So the largest challenge for us was in parallelization and processing all this data, how to divide it into chunks, how to collect everything together. And sorry, can I just go there? So, and assuming that the data is processed on the personal computer, it would take a crazy amount of years. So these type of tasks for us were successfully deployed in the microservices implementation for Amazon, like Lambda functions. And it turned out that given their modern limit of 15 minutes, it's really possible to do the reading, to do the processing, to do calculation of index, and to use them as features. All in 15 minutes for a given window of 1 by 1 kilometer, and then assembly this 1 by 1 kilometer chunks into the whole global map was the way to go solution. Back to these slides. So I collected the links to the data sets and links to the both UI and programmatic methods of how to most effectively process the satellite data, because the main challenge with it is geometrically corrected and geometrically positioned. So it's not only like just looking at the picture, but it's also looking at the picture and understanding where it is. And alignment of different data is the first part of the problem, is how to position it in the on the ground and collect different types of data within this ground. So I'm trying to collect in my GitHub links to these types of resources. So yeah, Lambda functions was really saving for us, and also I believe that Google Cloud Functions do pretty much the same thing, as like reading the time series of images all together and using them for the analysis. So it allows us to parallelize to up to 40,000 of data calls with a pretty convenient cost model, and it was possible to do the changes, updates, and the most important part for us was traceability, because before we moved to the serverless, for the instance type of implementation, for us it was really a nightmare how to manage this beast. So this is basically all I plan to say today, and feel free to check out my GitHub account. I try to pull different data sources with the links, which may be interesting for the agricultural monitoring or different type of mapping. Yeah. All right.
One question.
Yeah.
What's the most interesting application you did with this data? For you, what was the most interesting analysis?
We were trying to detect poppy seeds in Afghanistan. But the problem is that the poppy seeds are planted together with together with wheat. And they have exactly the same phenological phases. So it starts in the same part of the season and it grows like exactly the same time. So from the satellite picture, it's impossible to classify. So we tried hard, but without the hyperspectral data, it's simply impossible. That were really interesting.
Did you how did you verify that your detection was correct? Can you send something on the ground, into drones? How do you, so you detect the poppy seeds and wheat, right? So you know whether, you basically believe they're different. Can you verify it somehow?
So for that given application, we use the high resolution image, but it's only applicable when in the very end of the season when it's really visible what's going on there. But in most cases, we do the USDA data set for validation, though it's also somehow classified. But they use it like a part of semi-automatic classification.
So what's the next year looking for you? How is the next year?
For us, the crop classification problem was really more R&D, because for our team, what we do, we identify what kind of payloads to put to our satellites. And it turned out that for certain types of spectral bands, we see they are more applicable. So near-infrared, red age specifically for certain range for cotton, a certain range for wheat, and a certain range for corn and soybean. So instead of having a wide range imagery which has the same good pictures like Google Maps, instead of that we do hyperspectrum. Yeah.
So the data infrastructure is solely based on lambda functions right now. So when it comes to, I guess, high compute image processing applications such as this one, have you also looked into other, instead of using lambda functions, which are compute, which the resources are limited from compute perspective? So have you looked into maybe using GPU instances in an EMR cluster to do this sort of analysis and any performance comparisons that you think are?
As I said, so if we would put into production the crop classification model, and if we have to do it for the whole globe, yes, then we would need a GPU. But specifically for our type of applications, when we tell stories, when we try different bands, when our goal is not only provide this map, but also to make sure that our data is good for providing this map. So for us, still the price to value proportion of lambda functions was more relevant. So yes, in general terms, they are more expensive. But if you need only 1 million of invocations, then it's cheaper than having a GPU.
Did you try to predict, or did you consider to predict, let's say, the revenue, total revenue for the country or for the particular region based on the crop, different kinds of the crop, and after, at the end of the year?
Yes, we did. Unfortunately, I don't have a visible result right now, but it's a pretty straightforward problem once you utilize this data. So for example, USDA, it has, so for them, the life cycle of the crop looks like a waterfall. So some of the crop is seeded, some of the crop is growing, some of it's harvested, stored, sold, money get. And for all of these steps of the pipeline, they have their monetary values. So we are very, very much here because we know how much food was seeded and how much did it grow. And then we can predict the harvest. And we can predict the supply and demand. So this is basically the only thing which happened. And in this part of the analysis, there are so many other things which we don't have enough data to predict. So we see it, but we wouldn't have more valuable input than anyone else. So yeah, I'd say it's possible to see. So we have enough of the input data, but like God knows what happens here. All right. Any other questions? No. Thank you.